Hello everyone and welcome back to Bitewise Academy. In our previous lesson, we explored one of the most important components inside a computer, the motherboard. We learned that the motherboard acts as the main circuit board that connects the CPU, memory, storage devices, and input output devices, allowing them to work together as a complete system. But have you ever stopped to think about something? Even though all these components are physically connected to the motherboard, how do they actually communicate with one another? For example, how does the CPU know where your program is stored in memory? How does it retrieve the data it needs? How does it send information back to memory after performing a calculation? There must be some communication system that allows all these components to exchange information accurately and efficiently. And that communication system is exactly what we are going to learn in today's lesson. Today, we will explore one of the most fundamental concepts in computer architecture, the CPU bus. By the end of this lesson, you will understand how the CPU communicates with memory and other devices using three different buses: the address bus, data bus, and the control bus. We will also see why each of these buses has a unique responsibility and how they work together every single time your computer performs even the simplest task. So let's begin now. Before we jump into today's topic, let's quickly revisit what we learned in the previous lesson. We learned that the motherboard is much more than just a board holding different components together. It is actually the central platform that connects the CPU, RAM, storage devices, expansion cards, and input output ports. Think of the motherboard as the infrastructure of a city. A city contains houses, offices, hospitals, schools, and shopping malls. But these buildings become useful only because roads connect them. Without roads, people wouldn't be able to travel from one place to another. Similarly, inside a computer, simply placing the CPU, RAM, and storage on the motherboard isn't enough. These components constantly need to exchange information. The CPU may need to fetch an instruction from memory. Memory may need to send data back to the CPU. The CPU may need to store a calculation result back into RAM. All of this communication happens continuously, millions or even billions of times every second. So, today's question is, what are the electrical pathways that carry this information? How does the CPU tell memory exactly where to look? How does the actual data travel? Who decides when data should be transferred? The answer to all these questions is the computer bus. Today's lesson is all about understanding this communication system. Once you understand buses, you will have a much clearer picture of the how CPU interacts with rest of the computer. Let's see what exactly a bus is. Let's begin with a simple example from everyday life. Imagine a city bus. A city bus follows a fixed route. People from different locations board the same bus, travel to their destinations, and then get off. Now imagine what would happen if every passenger needed a separate road built just for them to. It would be impossible, isn't it? The city would become extremely crowded. Construction costs would be enormous, and maintaining all those roads would be nearly impossible. Instead, everyone shares the same transportation system. Computers use a very similar idea. Inside a computer, there are many important components. The CPU needs to communicate with memory. Memory communicates with input and output devices. Storage devices exchange information with the processor. If every component had its own dedicated set of wires connecting it directly to every other component, the motherboard would become incredibly complex. It would require a huge number of wires, making the system more expensive, harder to design, and much more difficult to maintain. Instead, computers use a shared communication pathway. This shared pathway is called a bus. A bus is a collection of electrical wires or printed circuit traces on the motherboard that allows different components to exchange information. A bus is a collection of electrical wires or printed circuit traces on the motherboard that allows different components to exchange information. Instead of creating separate connections between every pair of components, they all communicate through this common pathway. Now let's define it formally. A computer bus is a shared communication pathway that connects the CPU, memory, and input output devices, allowing them to exchange data and control signals efficiently. Notice the word shared. This is extremely important. The bus doesn't belong to only the CPU. It doesn't belong only to memory. Instead, every component that needs to communicate uses the same communication pathway. Of course, since many components share the same pathway, there must also be rules that determine who can use it and when. We will learn about those rules later in this lesson when we discuss topics like bus arbitration and control signals. Physically, a bus isn't a single wire. It is actually a bundle of many parallel wires or electrical traces printed onto the motherboard. Each wire has a specific purpose. Some wires carry addresses, some carry actual data. Others carry control signals that coordinate communication. This naturally brings us to one important question. If different kinds of information are traveling inside the computer, do they all use the same bus? The answer is absolutely no. To make communication organized and efficient, the computer uses three different buses, each with a specific responsibility. And that's exactly what we are going to explore in the next slide. Now that we understand what a computer bus is, let's ask an important question. Why do we even need a bus? Why not simply connect every computer component directly to every other component using separate wires? At first glance, that might actually sound like a good idea. Imagine you have only two people who need to talk to each other. Connecting them directly is simple. But now imagine a classroom with 30 students where every student needs a direct communication line to every other student. Suddenly, the number of connections grows enormously. It becomes confusing, expensive, and almost impossible to manage. The same thing would happen inside a computer. Think about the CPU. It needs to communicate with RAM, storage devices, the keyboard, mouse, graphics card, the printer, network devices, and many more components. If every one of these devices had its own dedicated wires to every other device, the motherboard would become extremely complicated. There would be thousands of electrical connections crossing over one another, making the system difficult to manufacture, expensive to build, and much harder to maintain. Instead, engineers use a much smarter solution, a shared communication pathway known as the bus. Let's look at the three major benefits. First, it simplifies wiring. Instead of creating a separate set of wires between every pair of devices, all components communicate using the same shared pathway. This dramatically reduces the complexity of the motherboard. Second, it standardizes communication. Every component follows the same communication rules, whether the RAM is made by one manufacturer and the CPU by another. They can still work together because they all use the same bus protocol for transferring address, data, and control signals. This standardization is one of the reasons computer components from different manufacturers are compatible with one another. Third, it enables modular expansion. Suppose you decide to increase your RAM from 8 GB to 16 GB or install a new expansion device. You don't need to redesign the entire motherboard or create a new set of communication wires. The new device simply connects to the existing bus structure and follows the same communication rules. This makes computers flexible, upgradable, and much easier to expand over time. So, the bus isn't just a convenient feature, it is one of the key reasons modern computers are practical, scalable, and affordable. Now that we know why the bus is so important, let's see something even more interesting. Although we use the word bus as if it were a single thing, it actually consists of three different buses, each performing a completely different job. Let's explore them one by one. We have learned that the CPU constantly communicates with memory and other devices. But here is something important to remember. Every communication doesn't happen through just one type of bus. Instead, three different buses work together and each one has a specific responsibility. Think about ordering a package online. First, you provide the delivery address. Then, the delivery company transports the package. Finally, there are instructions such as when to deliver, where a signature is required, or whether the package has been delivered successfully. Notice that these are three completely different kinds of information. A computer works in exactly the same way. Whenever the CPU communicates with memory, it needs to answer three questions: where, what, how, and when. These three questions are answered by three different buses. Let's start with the first one now. The first one is address bus. Answers the question where. Its job is to specify the memory location that the CPU wants to access. It simply tells memory where to look. The address bus always carries addresses from the CPU to memory or an input-output device. So its communication is one way or unidirectional. Next comes the data bus. This answers the question what. Once the correct memory location has been identified, the actual information, whether it is data or an instruction, travels through the data bus. Unlike the address bus, the data bus carries information in both directions. Sometimes the CPU reads data from memory, other times it writes data back to memory. Therefore, the data bus is bidirectional. Finally, we have the control bus. This answers the question how and when. Imagine trying to speak to someone while they aren't listening. Communication would fail even if you had the correct address and the correct message. The control bus solves this problem by carrying timing and command signals. It tells memory whether the CPU wants to perform a read operation or a write operation. It also coordinates when each transfer should begin and end. These signals can travel in both directions, making the control bus bidirectional as well. So remember this simple rule. Address bus tells where, data bus carries what, control bus manages how and when. If you can remember these three questions, you will understand almost every memory transfer inside a computer. Now let us study each bus individually, starting with the address bus. Let's begin with the first and perhaps the easiest bus to understand, the address bus. Imagine you want to send a birthday gift to your friend. Before the gift can be delivered, what is the first piece of information the courier needs? The address. Without the address, the courier has no idea where the package should go. The CPU faces the same situation. Memory contains millions or even billions of storage locations. When the CPU wants to read a piece of information or store new data, it must first identify the exact location in memory. This is the job of the address bus. The address bus carries only one type of information, the memory address. Notice something very important. It does not carry the actual data. Many beginners confuse the address bus with the data bus, but they perform completely different tasks. The address bus simply points to the location where the data is stored. The actual information will travel later through the data bus. You can think of it like writing an address on an envelope. The address tells the postal service where to deliver the letter, but the address itself is not the letter. Similarly, the address bus tells memory where the CPU wants to access information, but it does not carry the information itself. Another important point is that every byte of memory has its own unique numerical address. Every byte of memory has its own unique numerical address. This allows the CPU to access any required location quickly and accurately. Now let's talk about the direction of communication. The address bus is unidirectional. That means information flows in only one direction. The CPU sends address outwards to memory or input-output devices. Memory never sends an address back to the CPU. Why? Because the CPU is always the component that initiates communication. It decides which memory location should be accessed, and memory simply responds to the request. So whenever you hear address bus, immediately remember three key ideas. It carries addresses only. It tells memory where to read or write. It always travels from the CPU to memory or devices, making it unidirectional. In the next slide, we will go one step deeper and discover how the width of the data bus determines the maximum amount of memory a processor can directly access. So far, we have learned that the address bus tells memory where the CPU wants to read or write data. Now, let's answer a very interesting question. How much memory can a CPU actually access? Okay, how much memory can a CPU actually access? Is it unlimited? Can a processor access any amount of memory? The answer is no. The amount of memory a processor can directly access depends on one very important factor, the width of the address bus. But what exactly does width mean? Think of the address bus as a group of electrical lines running between the CPU and memory. Each line carries one bit of information. So, if a processor has a 16-bit address bus, it means there are 16 separate address lines working together. Similarly, a 32-bit address bus has 32 address lines, and a 64-bit address bus has 64 address lines. Now, here is the key idea. Every address line can carry either 0 or a 1. That means each line has two possible states. When multiple lines work together, the number of unique address combinations grows exponentially. This is why we use the formula 2 raised to the power n, when n is the number of address lines, because every line carries only two possible values, either 0 or 1. So if there are n number of lines, then the possible number of data that could be transferred is 2 to the power of n, where n is the number of address lines. Let's see how this works. If the address bus is 16 bits wide, the CPU can generate 2 to the power of 16 unique addresses. That equals 65,536 memory locations, which is approximately 64 kilobytes of addressable memory. Now increase the address bus to 20 bits. The number becomes 2 to the power of 20 or 2 raised to the power of 20, which equals 10,48,576 memory locations, or approximately 1 megabyte. Next comes the 32-bit address bus using the same formula, 2 raised to the power of 32. Okay. So it is 429 crores 496 lakhs 7,000. I'm sorry. It's nearly 4 gigabytes of address memory. Finally, consider a 64-bit address bus. The formula becomes 2 to the power of 64 or 2 raised to the power of 64, which is equal to 18.4 quintillion addressable locations. For practical purposes, we simply say that it provides an extremely large address space measured in exabytes. Now notice the trend. Every time we increase the width of the address bus, the number of possible memory addresses increases dramatically. This is why your slide ends with an important takeaway. A wider address bus allows the CPU to directly access more memory. Remember this carefully. The address bus does not make the computer faster by itself. Its primary job is to determine how much memory the processor can address directly. That's an important distinction because in the next few slides, we will meet another bus whose width affects speed, not memory capacity. So don't confuse the two. Let's now look inside the computer and see how the address bus actually operates between the CPU and memory. Now let's visualize how the address bus works inside a computer system. Instead of looking only at definitions, let's follow what actually happens when the CPU wants to access memory. Inside the CPU, there is a special component called the address register. You don't need to worry about all its internal details right now. For this lesson, simply remember that the address register holds the memory addresses that the CPU wants to access. That's it. Suppose the CPU needs to read an instruction stored at a particular memory location. The first step is for the CPU to calculate or obtain that memory address. Once the address is ready, the address register places that address onto the address bus. Now the electrical signals travel along the address bus towards memory. But memory contains thousands, millions, or even billions of locations. How does memory know which one of the CPU is referring to? This is where another important component comes into the picture, the address decoder. You can think of the address decoder as a receptionist in a large office building. Imagine someone arrives with an office number. The receptionist looks at the number and immediately directs them to the correct room. The address decoder performs a similar task. It receives the address coming from the CPU and activates only the required memory location. Every other memory location remains inactive. This ensures that the CPU communicates with exactly the correct location and nothing else. Notice something very important in this diagram. The arrows point only from the CPU towards memory. There are no arrows coming back. This clearly illustrates why the address bus is called unidirectional. The CPU always drives the address bus. Memory never sends addresses back to the CPU. Memory simply waits for the CPU to specify a location and then responds accordingly. That's why the key takeaway on this slide is so important, that the CPU always drives the address bus. Address information always flows in one direction from the CPU to memory or input-output devices. Once the correct memory location has been selected, the next question becomes how does the actual information travel? That brings us to our second type of bus, the data bus. So far, we have learned that the address bus tells memory where to find the required information. But here is an important question. Once the CPU has identified the correct memory location, how does the actual information travel between the CPU and memory? This is where our second type of bus comes into the picture, the data bus. Let's begin with a simple real life example. Imagine you have ordered a new laptop online. The first thing the delivery company needs is your home address. Without it, they won't know where to deliver the package. But once they know your address, does the address itself arrives at your home? Of course not. What actually reaches your home is the package. In a computer, the address bus is like the address written on the delivery label, while the data bus is like the delivery truck carrying the package. The data bus carries the actual information between the CPU and memory. This information could be a program instruction, a number that needs to be processed, a character you have typed, an image, a video, or any other form of digital data. Unlike the address bus, which only carries location information, the data bus carries the actual content that the CPU wants to read or write. Now, notice another major difference. The address bus always moves in one direction, from the CPU to memory. But the data bus works differently. Sometimes the CPU needs to read information from the memory. In that case, data travels from memory to the CPU. At other times, the CPU has processed some information and needs to store the result back into memory. Now the data travels from the CPU to memory. Since information moves in both directions, the data bus is called a bidirectional bus. This is one of the easiest ways to remember it. Address bus is one direction, data bus two directions. One more important point, the data bus carries both data and program instructions. Many beginners think it carries only data, but remember, every program stored in memory is made up of instructions, and those instructions also travel through the data bus when the CPU fetches them. So whenever someone asks what actually moves between the CPU and memory, the answer is the data bus carries the actual data and instructions. Now that we know its purpose, let's understand another interesting concept. Does every data bus transfer the same amount of data at a time? The answer is no. And that depends on something called the data bus width. Let's learn that what it means. Earlier, we learned that the width of the address bus determines how much memory the CPU can address. The data bus has a different role. Here, the width determines how much data can be transferred in one operation. Let us understand this with a simple analogy. Imagine two highways connecting the same two cities. The first highway has one lane. The second highway has 8 lanes. Both highways reach the same destination. However, which one can carry more vehicles at the same time? Obviously, the highway with 8 lanes. The same idea applies to the data bus. A wider data bus has more data lines, allowing more bits of information to travel simultaneously. Let's look at a few examples. An 8-bit data bus can transfer 8 bits, which is 1 byte, in one transfer cycle. This was common in many early microprocessors. A 32-bit data bus transfers 32 bits or 4 bytes during each transfer. This became common in many older desktop computers. Modern processors often use a 64-bit data bus. That means 64 bits or 8 bytes can be transferred during a single transfer cycle. Notice what happens as the width increases. The CPU doesn't necessarily become smarter. Instead, it can move more information at once. Imagine filling a bucket using a narrow pipe and then using a much wider pipe. The wider pipe fills the bucket more quickly because more water flows at the same time. Similarly, a wider data bus allows more bits to move together during each transfer. That's why your slide concludes with an important statement: more lanes mean more data transferred per clock cycle, which generally improves data transfer performance. Now, now it's important not to confuse this with the address bus. Let's compare them one more time. The address bus width determines how much memory can be addressed. The data bus width determines how much data can be transferred in one operation. These are two completely different concepts. We will revisit this comparison again near the end of the lesson because it's one of the most frequently asked interview questions. Now let us see how the data bus actually works inside the computer. The data bus structure. Now let us follow what actually happens during a data transfer. Inside the CPU, data is temporarily held in special high-speed storage areas called data registers. For this lesson, simply remember that these registers temporarily hold the information the CPU is processing. Let's imagine the CPU wants to read some data from memory. The CPU first specifies the required memory address using the address bus. Once memory identifies the correct location, it retrieves the stored information. Now comes the job of the data bus. The memory places that information onto the data bus. The electrical signals travel along the data bus until they reach the CPU. Finally, the data registers receive the information so the CPU can begin processing it. Now let us consider the opposite situation. Suppose the CPU has just completed a calculation. Maybe it added two numbers or finished executing an instruction. Now the result must be stored back into the memory. This time, the data registers place the result onto the data bus. The information travels from the CPU to memory, where it is stored in the appropriate memory location. Notice that the same data bus was used in both examples. The only thing that changed was the direction of travel. When reading, memory to CPU. When writing, CPU to memory. That's exactly why the data bus is called bidirectional. Take a look at the arrow in the diagram. Unlike the address bus, which had only one arrow pointing outwards, this diagram clearly shows arrows in both directions. That's the visual clue reminding us that the information can move either way depending on whether the CPU is reading or writing. So here is the key takeaway for this slide. The data bus is responsible for carrying the actual data and program instructions, and it allows communication in both directions between the CPU and memory. Now we have answered two important questions. Where should the CPU access? The address bus answers that. What information should be transferred? The data bus handles that. But there is still one question remaining. Who tells the CPU and memory when to start, when to stop, and whether the operation is a read or a write? That's the responsibility of our third and final bus, the control bus. So far, we have answered two important questions about communication inside a computer. The address bus tells memory where the CPU wants to access information. The data bus carries what information being transferred. But imagine this situation. Suppose memory starts sending data before the CPU is ready to receive it. Or imagine the CPU wants to write data into memory, but memory assumes it's supposed to send data instead. What do you think would happen? The communication would fail, obviously. Just like people need rules while communicating, computer components also need coordination. And that is exactly the responsibility of the control bus. Let us understand this with a simple real life example. Imagine a busy road intersection. There are roads, there are vehicles, but without traffic lights, everyone would try to move at the same time. Cars would collide, traffic would become chaotic, and nobody would know whose turn it is. Traffic lights solve this problem by controlling when vehicles move and which direction they should go. The control bus plays exactly the same role inside a computer. It does not carry memory addresses, it does not carry actual data. Instead, it carries command signals and timing signals that tell every component what operation is taking place and when it should happen. For example, the control bus tells memory the CPU wants to read data or the CPU wants to write data. It also uses the system clock to synchronize operations so that every component works together in the correct sequence. Notice another important point on this slide. The control bus is bidirectional. Some signals travel from the CPU to memory or devices. For example, the CPU sends read and write commands. At other times, devices send signals back to the CPU. For example, an input device might interrupt the CPU to request immediate attention, so information flows in both directions. That makes the control bus bidirectional. Now you can see why all these three buses are essential. An address bus says, go ahead and go here. The data bus says, here is the information. The control bus says, now is the right time and this is the operation to perform. Without the control bus, communication inside a computer would become completely uncoordinated. In the next slide, we will look at the most common signals carried by the control bus and understand what each one does. Let's examine some of the most important signals carried by the control bus. These signals act like instructions that coordinate every communication inside the computer. Let's look at them one by one. Read signal. Suppose the CPU needs information stored in memory. The CPU sends a read signal through the control bus. This tells memory, please send the contents of the requested memory location to me. Memory then retrieves the required information and places it onto the data bus. So remember, read means data travels from memory to the CPU. Read means data travels from memory to the CPU. Write signal. Now imagine the CPU has completed a calculation. Perhaps it has added two numbers or processed part of a program. The result must now be stored in memory. The CPU sends a write signal. This tells memory, I am sending you new data. Store it in the specified memory location. Memory accepts the incoming information and saves it. So, write means data travels from the CPU to memory. Next, clock signal. Every digital computer operates according to a timing mechanism called the system clock. Every digital computer operates according to a timing mechanism called the system clock. You can think of it like the conductor of an orchestra. An orchestra may have dozens of musicians, but everyone follows the conductor's timings so that the music stays synchronized. Similarly, the system clock keeps every operation inside the computer properly timed. It ensures that reading, writing, and processing happens in correct order. Without proper timing, components would operate at different moments, causing errors. Next, interrupt requests, IRQ. Now let's imagine you are studying quietly at home. Suddenly, the doorbell rings. You temporarily stop what you are doing and answer the doorbell. Something needs your attention. Computers work in a similar way. Sometimes an input or output device needs immediate attention from the CPU. Instead of waiting indefinitely, the device sends an interrupt request, commonly called an IRQ, interrupt request. The CPU then decides when to pause its current task and handle the device's request. Interrupts make computers responsive to external events like keyboard presses, mouse movements, or incoming data from peripherals. Next one is bus request or bus grant. Remember that many devices share the same communication pathway. If two devices try to use the bus simultaneously, conflicts would occur. So, a device first sends a bus request asking permission to use the bus. The system then sends a bus grant to the selected device, giving it temporary control. This ensures that only one device actively uses the shared bus at any given time. We will study this process in greater detail later when we discuss the bus arbitration. Next is reset signal. Finally, we have the reset signal. When activated, it returns the CPU or another component to a known starting state. This is useful during system startup or when recovering from certain type of errors. So, although the control bus doesn't carry data or address, these signals make it the coordinator of the entire communication process. Without these signals, the CPU, memory, and input-output devices would have no organized way to work together. Now, let's bring all these signals together and see how they move through the system. Inside the CPU, the control unit, often abbreviated as the control unit, is responsible for generating many of the control signals we have just discussed. When the CPU needs to perform an operation, the control unit sends the appropriate command onto the control bus. For example, if the CPU needs to retrieve information from memory, the control unit generates a read signal. If the CPU wants to store information, it generates a write signal. These command signals travel through the control bus to memory or an input-output device. Now look at the other side of the diagram. Memory and input-output devices contain device controllers. These controllers receive the commands sent by the CPU. They interpret those commands and perform the required operation. But communication doesn't stop here. Sometimes these devices also need to communicate back to the CPU. For example, they may send an interrupt request to indicate that they need immediate attention, or they may send an acknowledge signal confirming that an operation has been completed successfully. Notice once again how the arrows in this diagram point in both directions. Some signals originate from the CPU, others originate from memory or peripheral devices. This visual representation reinforces an important concept. The control bus is bidirectional because communication flows both to and from the CPU. The key signals shown in this diagram, such as memory read, memory write, system clock, interrupt requests, and bus grant or acknowledge, all work together to coordinate communication across the entire computer system. At this point, we have completed our study of the three fundamental buses. The address bus tells where communication should occur. The data bus carries what information is transferred. The control bus decides how and when the transfer takes place. Now that we understand each bus individually, it's time to see how they all work together inside a complete computer system. That's exactly what we will explore in the next slide. So far, we have studied the address bus, the data bus, and the control bus separately. Now let's put all the pieces together and understand how an entire computer system communicates as one integrated unit. Take a look at the diagram on your screen. Notice that there are three major sections. First, we have the central processing unit or the CPU. Second, we have the main memory, which is RAM. And finally, we have the input-output subsystem, which includes devices such as storage drives, keyboards, mice, displays, printers, and many other peripherals. These three sections constantly communicate with one another while your computer is running. Let's begin with the CPU. Inside the CPU, you can see several important components. The arithmetic logic unit, or ALU, performs calculations and logical operations such as addition, subtraction, multiplication, comparison, and decision making. The control unit, or CU, acts as the coordinator of the processor. It fetches instructions, interrupts them, and controls the sequence of operations carried out by the CPU. You also see registers such as MA MD and PC. At this stage, don't worry about learning every register in detail. For now, simply understand that registers are very small, extremely fast storage locations inside the CPU that temporarily hold information while instructions are being executed. Finally, notice the internal high-speed bus. This bus connects the internal components of the CPU, allowing them to exchange information quickly. Now, let's move to the second section, the main memory, or RAM. RAM stores the programs and data that the CPU is currently using. It consists of addressable data cells, meaning every storage location has its own unique address. This is exactly why the address bus is so important. The CPU can access any memory location because each one has its own unique address. The slide also shows a memory bus controller. You can think of it as a manager that helps coordinate communication between the CPU and memory. Now let's move to the third section, the input-output subsystem. This includes storage devices such as SSDs and hard drives, input devices like keyboards and mice, and output devices such as monitors and printers. Whenever you press a key, save a file, or display an image on your monitor, these devices communicate with the CPU through the system buses. Now let's focus on the three buses showing at the bottom of the diagram. The address bus carries address from the CPU to memory and input-output devices. Its job is simply to identify the required location. The data bus carries the actual information in both directions. It transports instructions, numbers, text, images, and every other form of digital data between the CPU and memory or devices. Finally, the control bus carries command and timing signals. It tells components when to perform a read operation, when to perform a write operation, and keeps everything synchronized using the system clock. Notice something very important. These three buses are not alternatives. Whenever the CPU communicates with memory, all three buses work together. For example, imagine you are opening a document stored in memory. First, the address bus identifies the correct memory location. Next, the control bus issues a read command and coordinates the timing. Finally, the data bus carries the requested information from memory back to the CPU. The operation succeeds only because all three buses perform their individual responsibilities at the same time. This is why the three buses are often described as working together as a team, each with its own specialized role. Now that we understand how the complete system is organized, let's look at something many beginners find confusing. When we say bus, are we always talking about the same physical bus? Actually, no. There are different levels of buses inside a computer. Let's understand the difference between internal and external buses. Up to this point, we have used the term bus quite generally. However, there is an important distinction that every computer science student should understand. Not all buses exist in the same part of the computer. Some buses are inside the CPU, while others connect the CPU to components outside it. Let's begin with the internal bus. As the name suggests, an internal bus exists inside the processor itself. It connects the CPU's internal components. Okay, let's begin with the internal bus. As the name suggests, an internal bus exists inside the processor itself. It connects the CPU's internal components such as the ALU, control unit and registers. Remember the internal high-speed bus we just saw in the previous diagram. That's exactly what we are talking about here. Because these components are located very close to one another, the physical distance is extremely small. A shorter distance means electrical signals travel very quickly, allowing communication inside the CPU to happen at extremely high speeds. Another important characteristic is that the internal bus is fixed. It is designed as part of the processor during manufacturing. As users, we cannot modify or expand it. Now let's compare that with the external bus. The external bus connects the CPU to the components inside the processor, such as RAM, storage devices, and input-output devices through the motherboard. Unlike the internal bus, these connections span a much greater physical distance. Signals have to travel across the motherboard, so communication is relatively slower than communication inside the CPU. This is completely normal and expected. The external bus is also expandable. For example, if you install additional RAM or connect new hardware, these devices communicate with the CPU through the external bus architecture. Here is an important point for this lesson. The address bus, data bus, and control bus that we have been studying are part of this external communication system between the CPU and memory or input-output devices. Remember, the address bus, data bus, and control bus that we have been studying are part of this external communication system between the CPU and memory or input-output devices. That's exactly what this slide is emphasizing. So don't confuse the internal bus with the three buses we have been discussing throughout this lesson. Think of it this way. The internal bus helps the CPU communicate within itself. The external bus helps the CPU communicate with the rest of the computer. Both are essential, but they operate at different levels of system. As we continue, you will notice another interesting challenge. If many devices share the same external bus, what happens if two devices tries to use it at the same time? Wouldn't their signals interfere with one another? The answer is yes. And engineers solved this problem using a technique called tri-state logic. Let's explore how that works in the next slide. So far, we have learned that the address bus, data bus, and control bus are shared communication pathways. Now let's think about an important problem. If many devices share the same physical wires, what happens if two devices tries to send signals at exactly the same time? Imagine two people trying to speak into the same microphone simultaneously. Instead of hearing one clear voice, you hear noise because both voices overlap. The same thing would happen inside a computer. If the CPU and another device both tried to place electrical signals onto the same bus at the same time, the signals would interfere with each other. The receiving device wouldn't know which signal was correct, leading to communication errors. So, how is this problem solved? Engineers use something called the tri-state logic. Let's understand the name first. Normally, a digital wire can carry one of two logical states, 0 or 1. Tri-state logic introduces a third state called the high impedance. High impedance, often written simply as HIZ. Think of this third state as being electrically disconnected. Imagine a classroom discussion. Only one student is allowed to answer a question at a time. Everyone else remains silent until the teacher calls on them. In this analogy, speaking represents sending a 1 or a 0. Remaining silent represents the high impedance state. Inside the computer, every device connected to the bus can either send a 0, send a 1, or remain completely disconnected from the bus. Only the device that has permission to communicate leaves the high impedance state and actively drives the bus. Every other device stays electrically disconnected. This simple idea prevents signal clashes and allows many devices to safely share the same communication pathway. Now let's move to the second concept on this slide, Bus multiplexing. Suppose a processor has a limited number of physical pins, wouldn't it be useful if the same wires could perform more than one job? That's exactly the idea behind bus multiplexing. Instead of having separate wires for addresses and data, some computer systems reuse the same physical lines. Here is how it works. First, those lines carry the memory address. Once the memory has received the address, the same physical wires are switched to carry the actual data. A control signal tells the memory whether these shared lines currently contain an address or data. Think of it like a railway track. During one scheduled time slot, the track is used by a passenger train. Later, the same track is used by a freight train. The track itself never changes, only its purpose changes depending on the schedule. Similarly, in bus multiplexing, the wires remain the same, but what they carry changes over time. This allows manufacturers to reduce the number of physical pins on a processor, making hardware simpler and more compact. So, this slide introduces two important engineering techniques. Tri-state logic prevents signal conflicts by allowing only one device to actively use the bus at a time. Bus multiplexing allows the same physical wires to carry different kinds of information at different moments. Now, this raises another important question. If only one device can use the bus at a time, who decides whose turn is it? That's exactly what we will study next. Now we have reached one of the most important coordination mechanisms in computer architecture, bus arbitration. Let's begin with a real life situation. Imagine four students arrive at the classroom door at exactly the same time. If everyone tries to enter together, they will all block the doorway. Instead, someone decides who enters first. Only after one student passes does the next student get a turn. The shared computer bus works in exactly the same way. Many devices may need access to the bus at nearly the same time. The CPU may need it, a storage device may need it, a network controller, an input output device may need it as well. Since only one device can actively use the shared bus at any instant, the system needs a method to decide who gets permission first. This decision making process is called the bus arbitration. The device responsible for making this decision is called the arbiter. Depending on the computer's design, the arbiter may be part of the control unit or it may be a separate hardware controller. Your slide introduces three common arbitration methods. Let's understand each one. Daisy chaining. Imagine students standing in a single line. Permission begins with the first student. If the student doesn't need to enter, permission moves to the next student and then the next. Eventually, it reaches the first student who actually needs to pass through the door. That's exactly how daisy chaining works. A grant signal passes from one device to another until it reaches a device requesting the bus. This method is simple, but devices closer to the beginning of the chain generally receive higher priority. Centralized arbitration. Now imagine the classroom has a teacher standing at the door. Instead of students deciding among themselves, every student asks the teacher for permission. The teacher chooses who enters next. Similarly, in centralized arbitration, every device sends its request to a single arbiter. The arbiter receives all requests and grants access according to the system's priority rules. This approach keeps control organized because one component makes every decision. Distributed arbitration. Finally, imagine there is no teacher at the door. Instead, all the students communicate with one another and decide who should enter first. That's the basic idea behind distributed arbitration. Each device contains its own arbitration logic. The devices cooperate and negotiate among themselves without relying on one central controller. This approach can improve flexibility, although it requires more coordination between devices. So remember the key idea. Bus arbitration doesn't move data, it doesn't carry addresses. Its only purpose is to decide which device gets temporary control of the shared buses. Without bus arbitration, multiple devices could try to communicate simultaneously, leading to signal conflicts and unreliable operations. Now that we know how devices take turns using the bus, let's look at another important question. Once a device receives permission, how is the timing of communication controlled? That's the focus of our next slide. We have already learned that the control bus carries timing signals, but not every computer coordinates timing in exactly the same way. There are two major timing models shown on this slide: synchronous communication and asynchronous communication. Let's begin with the synchronous approach. Imagine a group of dancers performing on a stage. Every moment is synchronized with the beat of the music. No one moves independently. Everyone follows the same rhythm. A synchronous bus works in exactly this way. Every device shares a common system clock. The clock acts like a metronome, creating regular timing pulses. Each stage of communication happens according to these clock pulses. Because every device follows the same timing, communication becomes predictable and relatively simple to design. That's one of the biggest advantages listed on your slide. A synchronous system is easier to coordinate because every device follows the same schedule. However, there is also a limitation. Imagine professional athletes forced to walk at the pace of a beginner. Even though they could move much faster, they must wait for everyone else. Similarly, in a synchronous bus, faster devices may have to wait for the shared clock cycle before continuing. Now let's look at the second approach, the asynchronous bus. Imagine two people carrying a heavy table. Instead of following a drum beat, one person asks, "Ready?" The other replies, "Ready." Only then do they lift the table. This is called a handshake. An asynchronous bus works using a similar idea. Instead of relying on one common clock, devices communicate through readiness signals. Once device indicates that it is ready, the other acknowledges the signal. Only then does the transfer proceed. The advantage is that each device operates at its own natural speed. A slower device doesn't force a faster device to follow a fixed clock schedule. However, this flexibility comes with a trade off. The control logic becomes more complex because every transfer requires this additional coordination. So let's summarize. A synchronous bus relies on a shared clock, making communication simple and predictable. An asynchronous bus relies on a handshake mechanism, allowing devices to communicate at their own speeds but requiring more sophisticated control. Both methods solve the same problem, coordinating communication, but they do so in different ways. Now we have learned how devices share the bus, how they take turns using it, and how their communication is timed. The next step is to watch a complete memory operation unfold. Let's see exactly what happens when the CPU reads data from memory one step at a time. Now we have reached the most exciting part of this lesson. So far, we have studied the address bus, data bus, control bus individually. But inside a real computer, these buses never work alone. They always work together. Let's follow a complete CPU read operation and watch exactly what happens. Imagine you have opened a web browser. To display the browser on your screen, the CPU first needs to fetch the program instructions stored in memory. How does that happen? Let's go through it step by step. Step 1. The CPU issues a read command. Everything begins inside the CPU. The processor has decided that it needs information from memory. Before any data moves, the CPU sends a read signal through the control bus. Think of this as the CPU politely informing memory, "I am about to request some information. Please get ready." Notice that no address and no data have been transferred yet. The CPU is simply announcing that the type of operation that is about to take place. This is why the control bus is responsible for coordination. Step 2. The CPU places the address on the address bus. Now the CPU tells memory exactly where to look. It places the required memory address onto the address bus. Imagine walking into a library. Before the librarian can hand you a book, you first tell them the shelf number or call number. Similarly, the CPU specifies the exact memory location where the required instruction or data is stored. The address bus carries only this location information. It still does not carry the actual data. Step 3. Memory places the requested data on the data bus. Memory receives the address. It identifies the correct storage location. Then it retrieves the required information. Now the data bus becomes active. Memory places the requested data or instruction onto the data bus and the information begins traveling towards the CPU. This is the first time during the operation that the actual content moves. Notice something important. The data bus is moving from memory to the CPU because this is a read operation. Next, step 4, the CPU receives the data. Finally, the CPU receives the information through the data bus. The control bus confirms that the transfer has completed successfully. The processor can now begin executing the instruction or processing the data it has just received. The read operation is now complete. Let's quickly review what happened. The control bus announced the operation. The address bus specified the memory location. The data bus carried the requested information back to the CPU. Every successful read operation follows the same sequence. That's why all 3 buses are essential. Without any one of them, communication would fail. Now let's see what changes when CPU wants to write information back into the memory. A write operation is very similar to a read operation. However, one important thing changes. Instead of retrieving information from memory, the CPU is now sending information to memory. Let's imagine the CPU has just finished calculating the total marks of a student. The result now needs to be stored in memory. Let's see how that happens. Step 1. The CPU issues a write command. Just as before, communication begins with the control bus. This time, instead of sending a read signal, the CPU sends a write signal. This informs memory, I'm going to send you some new information, prepare to store it. Again, notice that no idea has moved yet. The CPU is simply specifying the type of operation. The CPU places the target address. In the next step, step 2, the CPU places the target address on the address bus. Next, the CPU specifies where the information should be stored. It places the destination memory address onto the address bus. Memory now knows the exact location where the incoming data belongs. Once again, notice that the address bus carries only the address, not the data itself. In step 3, the CPU places the data on the data bus. Now comes the major difference between a read and a write operation. During a write operation, the CPU itself places the data onto the data bus. The information now travels from the CPU towards memory. The data bus is still carrying the actual information, only the direction has changed. Memory stores the data. Memory receives the incoming information. It stores the data at the address specified earlier. Finally, the control bus confirms that the write operation has completed successfully. The write operation is now finished. Now let's compare read and write. Notice something interesting. The address bus never changes direction. It always travels from the CPU to memory. The control bus continues coordinating the entire operation. The only bus that changes direction is the data bus. During a read operation, memory to CPU. During a write operation, CPU to memory. That's one of the easiest ways to remember why the data bus is called bidirectional. Now that we understand how communication takes place, let us answer one final technical question. How do the sizes or widths of the buses affect the overall computer system? Earlier in this lesson, we learnt that both the address bus and data bus have widths measured in bits. However, they influence the system in completely different ways. Let's begin with the address bus. Remember the formula 2 to the power of n, where n is the number of address lines. A wider address bus allows the CPU to generate more unique memory addresses. That means the processor can directly access a large amount of memory. So, remember the simple relationship. Wider address bus is more addressable memory. Now, let's look at the data bus. Now, the data bus determines how many bits can travel during a single transfer. If the data bus is wider, more information moves in one transfer cycle. As a result, data transfer becomes more efficient. So, the relationship here is different. Wider data bus is more data moved per transfer. Notice that these are two completely independent ideas. A processor might have a 32-bit address bus, allowing it to address approximately 4 gigabytes of memory, while using a 64-bit data bus, allowing it to transfer 8 bytes of data in one transfer. These two widths do not have to be the same. That's a point students often misunderstand, so it's worth remembering. Finally, let us talk briefly about the control bus. Unlike the address bus and data bus, we don't usually describe the control bus in terms of a width that determines memory capacity or transfer size. Instead, we think of it as a collection of different signal lines such as read, write, clock, and interrupt signals that coordinate communication between components. So each bus contributes to system performance in its own unique way. The address bus determines how much memory can be addressed. The data bus determines how much information can be transferred at one time. The control bus ensures that every operation happens correctly and at the right time. At this point, we have built a complete understanding of how buses communicate. In the next section, we will connect these ideas to a real-world computer system and discuss the practical advantages and limitations of bus architecture. We have spent the entire lesson understanding the address bus, data bus, and control bus individually. Now let us see how these components appear in a real computer system. Imagine a modern desktop computer. At the center of the system in the CPU, connected to it is the main memory or RAM. Between these two components, communication takes place through the three buses we have studied throughout this lesson. Let's begin with the address bus. In this example, the CPU uses a 32-bit address bus. That means it can generate 2 to the power of 32 unique memory addresses, allowing it to directly address approximately 4 gigabytes of memory. Every time the CPU wants to access information, it first places the required memory address onto these address lines. Remember, the address bus always carries information from the CPU to memory. Its direction never changes. Next comes the data bus. This example uses a 64-bit data bus. That means 64 bits or 8 bytes of information can be transferred during a single transfer operation. Whenever the CPU reads information from memory, the data bus carries the information towards the processor. Whenever the CPU writes information back into the memory, the same data bus carries the information in the opposite direction. Finally, notice the control bus. Although it isn't shown with a numerical width like the other buses, it carries several important signals, including read, write, clock, and interrupt request. Together, these signals coordinate every communication between the CPU and memory. Now, pay attention to the note at the bottom of the slide. This diagram is intentionally simplified for learning purpose. Real computer systems are more sophisticated. Modern processors include multiple levels of cache memory, dedicated memory controllers, and additional communication technologies such as the PCI Express, commonly known as PCIe, for connecting high-speed devices like graphic cards. However, despite these additional technologies, the fundamental ideas you have learned today remain exactly the same. The CPU still needs to identify a memory location. The actual information still needs to travel. The communication still requires proper coordination. Those three responsibilities are handled by the address bus, data bus, and control bus. So, even in today's advanced computers, these basic principles continue to form the foundation of communication. Now, every engineering design has strengths and limitations, but bus architecture is no exception. Let's begin with the advantages. The first advantage is simplicity because multiple devices share the same communication pathway. The computer requires far fewer physical wires. This makes the motherboard easier to design and less expensive to manufacture. The second advantage is easy expansion. Suppose you decide to install additional RAM or connect another compatible device. Since the new hardware communicates through the existing bus structure, there is no need to redesign the entire communication system. This flexibility is one of the reasons personal computers can be upgraded so easily. The third advantage is standardization. Different manufacturers can produce CPUs, RAM modules, storage devices, and peripherals that still work together because they all follow common communication standards. Now let's look at the limitations. The biggest limitation is that only one device can actively use the shared bus at a time. If multiple devices need access simultaneously, some of them must wait. This waiting can reduce overall performance. Another limitation is the bus bottleneck. As more devices compete for access to the shared communication pathway, the bus may become congested. Even if individual devices are very fast, they still have to wait for the bus access. Finally, because many components depend on the same communication pathway, a fault affecting the bus can potentially disrupt communication throughout the system. Now, let's discuss the important concept mentioned at the bottom of this slide, the von Neumann bottleneck. According to your presentation, this bottleneck occurs because the CPU and memory share one communication pathway for both instructions and data. As a result, the CPU sometimes has to wait for memory transfer before it can continue processing. This waiting limits the overall speed of the system. Notice how this connects everything we have learned. The buses make communication possible, but because communication is shared, they can also become a limiting factor. Understanding both the strengths and limitations of the bus architecture gives us a balanced view of why computer engineers continue to develop faster and more efficient system designs. Before we finish today's lesson, let's quickly revise the most important terms we have learned. These are the definitions you will often encounter in textbooks, examinations, and interviews. Let's go through them one by one. A bus is a shared communication pathway that carries data or signals between computer components. Bus width refers to the number of parallel lines in a bus, which determines its communication capacity. The address bus is a unidirectional bus that carries memory addresses from the CPU to memory or input-output devices. The data bus is a bidirectional bus that carries actual data and program instructions between the CPU and memory. The control bus carries command and timing signals such as read, write, clock, and interrupt signals that coordinate communication. Bus arbitration is the process of deciding which device gains control of the shared bus when multiple devices request access. The tri-state buffer is a circuit that can output a logical 0, a logical 1, or enter a high impedance state, allowing multiple devices to safely share the same communication lines. Finally, multiplexing refers to reusing the same physical communication lines for different purposes at different moments in time. If you understand these terms clearly, you have already mastered the vocabulary needed to discuss CPU bus architecture with confidence. Let's finish the lesson with one final summary. Remember these three simple questions. Whenever the CPU communicates with memory, ask yourself where. The answer is the address bus. It carries memory addresses. It is unidirectional. Its width determines how much memory the processor can directly address. Next, ask what. The answer is the data bus. It carries the actual data and program instructions. It is bidirectional because information moves in both directions. Its width determines how much information can be transferred during one operation. Finally, ask how and when. The answer is the control bus. It carries read, write, clock, interrupt, and other control signals that coordinate every communication between the CPU, memory, and devices. If you can remember these three questions, where, what, and how, when, you will never confuse the three buses again. Now test yourself. There are some practice questions and the answers given here. If you think this video is helpful, please like, subscribe, and share the video with your friends. Thank you for watching. In the next lesson, we will continue building our understanding of computer architecture with another exciting topic. Until then, keep learning. Thank you so much.